So now let's move on to the numerical problems of the rolling operation. Let's start with it. So what it says, a 300 millimeter wide strip and 25 millimeter thick is fed through a rolling mill with two powered roll mills. So we now have kind of the roll mill, that is a two high rolling mill. Each roll is of radius 250 millimeter. The work thickness is to be reduced to 22 millimeter in one pass, right? So work thickness is to be reduced to 22 millimeter in one pass at a roll speed of 50 revolutions per minute. Then it goes on, the work material has a flow curve, that is K, the strength of the material equals to 275 megapascals, and the strain hardening coefficient of 0.15, and the friction coefficient is assumed to be 0.12, right? So what do we get? What kind of rolling operation is this one? You have to answer in the group. Based on the friction coefficient it is assuming, and we have discussed the various range of friction coefficient for different kind of temperature working. Now what it says, determine if the friction is sufficient to permit the rolling operation to be accomplished. If so, calculate the roll force, torque and horsepower. So first and foremost we have to calculate, first and foremost we will make a data, then we'll calculate the draft it is producing in a single step. So it says a 300 millimeter wide strip, a strip that is 300 millimeter wide and 25 millimeter thick, right? That is 300 millimeter and 25 millimeter thick. So we have the width, initial width, and we have the initial thickness here, right? So in a single pass, its thickness is reduced to 22 millimeter, right? So the draft we will have was initial thickness minus the final thickness. So in a single pass its thickness is reduced to 22 millimeter, so we have 25 minus 22, that is 3 millimeter. This is the draft that is required to be produced. Now we will calculate the maximum possible draft based on the roll radius and the friction between them. So we know that d max is equals to mu square into r. So what is the mu square r or m square r? M is 0.12 square and the r is, we have 250 millimeter. So the value is 3.6 millimeter. So based on this roll radius and the amount of friction between the work part and the roll, this is the maximum possible draft that can be produced in a single pass, right? And obviously it is more than what is required to produce, so it means we can perform this operation. Now we have verified that this operation can be performed based on the roll radius. Now we know it is possible, so calculate the roll force, torque and the horsepower. So what was the formula for the roll force? That was the average flow stress into width, right, into the contact length. And what was the formula for the torque? That was 0.5 force into the contact length. And the formula for the power, that was 2 pi n fl. So we have to calculate these three. So for the force, we need to determine the average flow stress, that is K strain to the power n 1 plus n We know the k, we know the n, value of n. Now what is left is exponent n, right? So now this is the formula for the average flow stress. As you know that the work part is being reduced, is being deformed gradually, so we are using the formula for the average flow stress. In the case of rolling, we have k as a flow curve or the strength constant. We have the strain hardening coefficient, that is 0.15, and only thing left is the true strain we need to determine. So what was the value of the true strain? It was ln of initial height divided by final height, h naught by h, or we can simply write ln of 25 by 22. So the true strain in this case would be 0.128. It's right. So this is the value of the true strain. Now we'll put it in the formula. We will have yf equals to 275 as a strength coefficient into 0.128 exponent 0.15 as a strain hardening exponent divided by 1 plus 0.15. So we can calculate this one. It would be around 175.7 megapascals. So this is the value of the flow stress, the average flow stress that is required. Now using this value, the flow stress, in the formula for the force, we will have 175.7 into the width of the work part, that is 300, right, into the contact length. We have to calculate the contact length as well. So what was the formula for the contact length? It was equals to under root r into initial thickness minus final thickness. So we will have under root 250 into 25 minus 22, that is 3 millimeter. So it would be equals to 27.4 millimeter. So this is the contact length. This is the contact length, and this is the flow stress. So we can simply write here 27.4. So the value of the force that is required to perform this rolling operation, it would be 1,444,786 Newton. So this is the force required to perform this rolling operation. So for the torque, we will have 0.5 into the force into the contact length. Contact length was equals to 27.4. So we will have 19786 Newton meter. Based on that torque, we can calculate the power, that is equals to 2 by, what is the value of n here? We have the value of n equals 50 revolutions per minute. So 2 pi into n into the force 1,444,786 into the contact length, that is 27.4, right? So we will have the value of power, that is equals to 12 into 432 into 0.86 Newton meter per minute. That would be Newton millimeter. We will have to divide it by 1000 to convert into the meters. We have to divide it by 1000, because this value is in millimeter. We have converted our answer into the meter, so that would be Newton meter per minute. This is the power that is required to power those rolls. So we can convert it into the horsepower for the sake of comparison. So as we know, if we convert it into the watts, Newton meter per second, sorry, for the sake of watt, we can multiply it by 60. So to convert this Newton meter per minute into the watts, that is Newton meter per seconds, we have to divide this value by 60. So it would be equals to 207,201 Newton meter per seconds. So we have the watts now. So and now to convert the watts into horsepower, we will simply divide it by 745.7, right? As 1 horsepower equals to this amount of watts, so the total horsepower for this rolling mill is 278 horsepower. So now we have calculated the force required, we have calculated the torque that was required, and the power. So it can be seen from the example that the large force is required to power the rolls requiring, and there are certain ways by which we can reduce this large amount of force. As you can see here, this force depends upon the YF, that is the flow stress. We cannot alter the flow stress because the strength constant of the material will remain same. We cannot change it. Our strain that is to be produced, we can change this one if we reduce the amount of draft that is required in a single step. If we perform let's suppose I want to reduce 3 millimeter in total, so and the maximum possible draft in each pass is 3.6 millimeter. So instead of performing this operation in a single draft, I can make 3 passes, each pass of 1 millimeter. So let me erase this last one so that we can write. steps reduce force and power required. Okay, so first one, we can reduce draft. Okay, so we can reduce the draft that is required in a single step. Instead of reducing 3 millimeter in a single step, we can reduce 1 millimeter in each pass, and you can perform 3 passes. So what will happen if we have reduced the draft? We will have a lesser strain, because our strain for this single step would be 25 by 24, and because of that the lower amount of flow stress will be required. First one, as we know, the force depends upon the flow stress. Second one is the contact length. As you know, the contact length also depends upon the this draft, so it will also reduce. Second thing is, if we can reduce the roll diameter. If you can reduce the roll diameter, it will also help to reduce the force. As you can see, the contact length depends upon the roll radius. Then third one, as we know that it depends upon the strain hardening coefficient, and that was equal to 0.12. In this case, it means it was somewhat cold working operation. That's why we require higher amount of forces. If you perform the same operation using the hot working, so the strain hardening coefficient would have been 0.4, or around the 0.4. So it means the flow stress value would be lower, because right, and ultimately we will have to have a lower force. So reduce draft, you can say reduce roll diameter. Second way, um, perform as hot working. You can perform it as a hot working, and yeah, we can reduce the lower roll speed. It will also reduce the power required. So these are some common tips to reduce the power and the force required to perform a rolling operation. Now let's move on to the second numerical. What it says, 2 millimeter thick slab is 10 inches wide and 12 feet long. So we have a slab that is 2 inches thick and just 10 inches wide, and it's 12 foot long. So we have a slab that is 2 inches thick and 10 inches wide, and we can say that is 12 foot into 12 inches. That would be 144. So that is 144 inches long. That is equals to 144 inches in length. Now it says thickness is to be reduced in 3 steps, right? In a hot rolling operation, each step will reduce the slab to 75% of its previous thickness. So let's suppose in step 1, final thickness would be 0.75 into the initial thickness. Each step will reduce the slab to 75% of its previous thickness. It is expected that for this metal and reduction of the slab will widen by 3%. So we have studied by empirical law it is around 2%. Now in this case the slab is widening or spreading by 3%. If the entry speed of the slab in the first step is 40 feet per minute, right? The entry speed of the slab in the first step is 40 feet per minute, and the roll speed is same as for the three steps, means VR is same for all steps. Determine length and exit velocity of the slab after the final reduction. So what would be the length of the slab and exit velocity of the slab after the final reduction? So we can directly write after 3 passes which we have to perform, the final thickness would be 0.75 for the first pass, 0.75 for the second pass, or 0.75 for the third pass into the thickness, that is 2 inches. So our value would be okay, so it will be reduced to around 0.844 inches. Now it says it is widening by 3% in each step, so the final width would be 1.03 into 1.03 into 1.03 into the 10 inches. So that would be around 10.927 inches. So this is the final dimensions of our slab. As you know, by constancy of volume, we have T naught, W naught, L naught. It would be equals to TF, WF, LF. So what is the value of these one? We have 2 into 10 into 144, that is equals to TF, that is 0.844 into WF, that is 10.927 into the final length. So by this we can calculate the final length. So our final length would be around 312.3 inches. We can divide it by 12 to get the foots, that is 26.025 feet. Now this is the first part which we have solved. Now it says determine the exit velocity of the slab after the final reduction. So after the final pass, determine the exit velocity. So we have VF, right? As we know, we can divide it by the time and we can convert into the initial velocity and the final velocity by the constancy of volume. So we have VF equals to 2 into the 10 into 40, that is the initial speed, that's 40 feet per minute. And this whole divided by the 0.75. This is for the first step, reduction in the thickness only to the 75%, and the spread in the width so that would be equals to 51.6 0.78 feet per minute, and it's for the first step. You can just say first pass. For the second pass, we can write it as Vf. This is the exit velocity of the first pass. For the second pass, we have now in the second pass, the initial thickness would be the final thickness of the first pass. The initial thickness of the second pass would be the final thickness of the first pass. You can see here, let's suppose we have a rolling mill. We have the first rolling pair, the second rolling pair, and the third rolling pair. So now once after it has passed from this roll, its thickness has been reduced. So for these rolls, its final thickness would be the initial thickness of this roll. Right, now the final thickness of this roll would be the initial thickness for the third one. Right, now so for the second pass, the initial width and the thickness would be the final width and thickness of the first pass. So we can write it as 0.75 into 2 into 1.03 into 10 inches and into the 40. Right, this whole is divided by now 0.75 into 0.75 into 2. This is the final thickness into 1.03 into 1.03 into 10. So we will have the value equals to again the 51.75 feet per minute. This is for the second pass. Now for the third pass, you can again perform this one. Now this will be the initial thickness and the length for the third pass, and for the final length and thickness, for final width and thickness of the third pass would be 0.75 into 0.75 into 0.75 multiplied by 2, and the width would be 1.03 multiplied by 1.03 into 1.03 multiplied by 10. That would be the final width and thickness of the third pass. This is how we can calculate the velocity, the exit velocity of after each passes. Now let's move on to the another problem. It says a series of cold rolling operations are to be used to reduce the thickness of a plate from 50 mm down to 25 mm. In a reversing to high mill, the roll diameter is 700 mm, so we have the R equals to 700 mm, and the initial thickness is 50 mm, final thickness is 25 mm, and the friction coefficient between the roll and the work is 0.15, so we can write M as 0.15. The specification is that the draft is to be equal on each pass. There is a condition that draft should be equal on each pass. Determine minimum number of passes required and draft for each pass. So we have to reduce this thickness into this one, and we have the roll diameter in the mill that is constant, we have the friction that is constant. There's a condition that the draft should be equal in each pass, and the second one is the value of the draft for each pass. So first of all, based on this roll diameter and the radius, you will simply calculate the maximum draft possible. That would be d max. D max equals to m square into r. That is, what is the value of m? 0.15 square into the 700 millimeter. There's a problem. It's a roll diameter of 700 millimeter, and sorry, that is for the roll, so the radius would be 700 by 2, right? So our maximum draft possible for this arrangement is 7.875 millimeter. So this is the maximum amount of draft that is possible in this case. Now we have to calculate the minimum number of passes, determine the minimum number of passes that are required. So minimum number of passes required, it can be calculated as total draft that is possible that we require is T naught minus Tf divided by the maximum possible draft in each pass. So total draft that we require is 50 minus 25, that is 25 millimeter, divided by 7.875. So it will be 25 divided by 7.875 millimeter. So the number of passes would be 3.17. So there's a minimum number of passes. This is the amount of draft that is required to be produced. It should be reduced from 50 to 25 millimeter. But the maximum possible reduction that we can produce in a single step is 7.875. So we assume that if we are producing maximum reduction in a single step, so the number of steps we will require would be the total reduction required divided by maximum possible required in each step. So this value is 3.17. So we will reduce it, we will move it towards the whole number value. So it can be changed from 3.17 to the 4 passes. And you might ask why it is not rounded up to 3 rather than 4, because it's about number of passes. We can perform 3 passes, but to produce this amount of draft, it requires 3.17. So we cannot reduce it to 3 because we will be left with some amount of draft. So we rounded it up to the upper value, that is the 4 passes. So this is the minimum number of passes that are required for this draft. Now to calculate the draft per pass, that is D equals to 50 minus 25 divided by 4. So if you are producing this amount of draft in total, and we are using these number of steps, so the total amount of draft in a single step would be this one, that is equals to 6.25 millimeter, right? So now we have calculated the minimum number of passes required, we have calculated the draft per pass. Now let's move on to the last numerical of our rolling problems. It says a plate that is 250 millimeter wide and 25 millimeter thick. It is to be reduced in a single pass. Just draw a plate. It says a plate that is 25 millimeter thick and 250 millimeter wide. So we have 25 millimeter and that is 250 millimeter. It is to be reduced in a single pass in a 2 high rolling mill to a thickness of 20 millimeters. So we have 20 initial thickness as 25. The final thickness that is to be reduced is 20 millimeter. The roll has a radius of 500 millimeters. So the roll radius we have is 500 millimeter, and its speed is VR, is the roll speed is 30 meter per minute. Right? The work material has a strength coefficient that is K equals to 240 megapascals, and the strain hardening exponent, that is N equals to 0.2. Now it asks determine the roll force, the roll torque, and the power required to complete this operation. So again, the first and the foremost step, calculate the draft that is required. The draft that is required is 25 minus 20, that is 5 millimeter. This is the total reduction that we need to produce in the slab. Now the second step, we will have to calculate the contact length. We have to calculate the contact length, that is equals to under root roll radius into the draft, that is C0 minus TF. So it would be under root the roll radius is 500 millimeter, so 500 into 5, so the value would be 50 millimeter. Now, as we know, the force equals to YFWL, and YF has a true strain value. The flow stress, for the flow stress we need to calculate the true strain, so the true strain would be equals to ln of initial thickness divided by final thickness, which would be around 25 by 20. So the true strain value is 0.223. So this is the value of the true strain. So the average flow stress would be, as we know, the strain coefficient into the true strain exponent strain hardening divided by 1 plus n. As a rolling operation, that's why we are using the average flow stress. So it would be equals to 240 into the 0.223 exponent strain hardening, that is 0.2 divided by 1 plus 0.2. So it would be equals to 148.1 megapascals, right? So now we have the average flow stress, we have the value of the contact length, we know the width, so we can calculate the rolling force. So rolling force would be YF is 148.1 into W, that is 250 into the contact length, that is 50. So the rolling force that is required is 1851829, right, newtons. This is the rolling force that is required. The second one, it says calculate the torque, that is equals to 0.5 into FL. So we have 0.5 into 1851829 into the contact length, that is equals to 50 millimeters. So we also convert it to the meters. For the standard value, we will divide by 1000. So the torque value would be equals to 46296 Newton meter, right? So now we want to calculate the number of revolutions per minute for the power. As you know, power equals to 2 pi n fl. We have all the values except the n, so for the sake of n we can get the n value. N equals to 30 meter per minute into 2 pi into 0.5. Convert into the revolutions per minute. So we have 9.55 revolutions per minute. So this is the value for the revolution per minute, or we can convert it into seconds divided by 60. So we will have around 0.159 revolutions per second. Right? So using this we can calculate the power, that is 2 pi into 0.159 into the force, that is 1851829 into the contact length, that is 50, and again it's in meters, millimeters, so we will convert it to the meters. So the power would be is equals to 92591 Newton meters per second. Right? So this is the third requirement. So that's all for the rolling operation. We have seen in the previous lecture, we have performed analysis of the rolling operation and discussed the various aspects of it, and in this short lecture we discussed about we have solved various numerical problems from our exercise in the book. Should you have any question, you may reach me at the Google Classroom.